I would have like Doritos or anything. I think he'd just be like, "Bro, you have bread?" I'd be like, "Yeah." He'd be like, "Okay, come on."
What else? Dude, I know you told me. Why? Oh, so two is outside and H would do Mexico. No, H is outside. Oh.
Somehow I did.
Then I got one question.
That is why bro.
Yeah, I did.
That's not, oh yeah, sorry.
Yeah. Yes, did
Wait,
a question.
yeah, you're
Sorry, I have my phone on me.
In such the Y value ranks. So.
Those are my last names.
Right, you got it.
Right?
And you didn't get that right.
Okay, but.
The most fun I
It's just a game test.
I still see in the backing, but.
Oh, you did a hotel to like.
Wait, that was.
I think this is my.
I don't understand. I just don't understand how you use case.
I was for the summer. Like I'm looking at.
Like, just
Okay, let's go to page 8. In your packet.
Do we get a picture? Is this the?
Just the note packet, yeah. So you can grab a classroom copy, just don't write in it. Okay, so this is curve sketching unit here. This is unit 5. So over the course of this unit here, we're going to, after we get through our theorems, we're going to talk about things that will help us identify or help us curves or sketch curves. So we'll get information about the first and second derivative and be able to sketch a curve, and we'll interpret a derivative graph as well. And then we'll end up with our final topic, which is optimization. It's kind of word problem like, similar to related rates, but really you're just find the derivative, find the critical point, and then using that critical point to find your answer. So this unit is just going to be a quiz unit. Right? So we're not going to have a test on this unit. So it'll just be a quiz, and we'll have that quiz that first week of October. Right. Does anybody know what the significance of this unit is in terms of where we are in our in the AB curriculum? This halfway point. Yeah. So after this, we're done with first semester AB topics, and we're moving on to antiderivatives. So we're going to start antiderivatives unit next, and then that way we can finish all of AB content by December, and then or November, because I want December for us to look at FRQs, to look at some mock practice AB tests, and then next semester will just be BC content. Okay. All right, so page 8. So let's start off with mean value theorem. So mean value theorem is, let me just read this statement out here. If a function is continuous over the interval from A to B and differentiable over the interval from parentheses A to B, so that means we're now moving into something where we're trying to guarantee a specific slope value. Before, we were just trying to guarantee a specific numeric value on the graph. Intermediate value theorem did that. We're trying to, if we knew a lower and higher y value, then we knew that we could guarantee any y value that sits in between. And then with extreme value theorem, we're trying to find an absolute max and absolute min. So we're looking for physical locations that are either the highest or lowest or in between. Now we're looking for a specific slope value. And because we're looking for a value that has a specific slope, we need additional conditions. So the conditions is we need the graph to be connected, no breaks in the graph. So and we've been seeing this, right? Every theorem that we've been introduced to needed that continuity statement. But the next two theorems requires an additional statement, and that is we need the graph to not only be connected, but we also need the graph to be smooth. So it needs to be differentiable over the interval. But the notation is a little bit different. The requirement for the smooth curve is only parentheses, but then the need for continuity is always with brackets. So continuity is always with brackets, but if you see anything with differentiable, it's going to be with parentheses. So that's just a subtle thing to make note of. So if we can get these two out of the way, and by the way, if like I would say like 80%, 90% of the time, if you can get the first condition to pass, you can get that second condition to pass as well. So they mostly go hand in hand. I'll talk a little bit later about some exceptions where it'll pass the first one, but not the second. But for now, let's just say that if you can get the first one to pass, you can almost ensure that the second one passes. Okay, for now. And then I'll talk about some exceptions later. So for now, if you can get the graph to be connected, then you can just go ahead and make that second statement. Now, if I can get two conditions to pass, then we can guarantee this. We can guarantee that whatever slope I find between the two endpoints, okay, and then the endpoints will always be provided for you. We just find the slope. So that's this right here, f of b minus f of a over b minus a. So that slope between two endpoints could be 2, it could be 1/2, could be -2, could be -3. Whatever slope I find there between two endpoints, I can guarantee that the slope is that slope I found is going to show up again somewhere on the curve at an exact point. Okay. So you can imagine this, right? That if I can see that there's a slope of 2 here, I can guarantee that the graph is also going to experience that slope of 2 there. So what we do is we find the slope between the two endpoints, we set it equal to the derivative, and then we ask the derivative to tell us the location where that specific steepness on the curve is occurring. Okay, so the formula is going to be set up this way. Okay, so three things here. Mean value theorem. We have to state our function is continuous on a closed interval. We have to state that the function is differentiable on the open interval, and then we find the slope at the endpoints. We set it equal to the derivative, and then we solve for x, and we look for that guaranteed slope somewhere along the curve. Okay, so let me work through a problem from scratch so you can see all the steps here. But oh, and then sometimes on AP exam, they may not say, hey, use mean value theorem for this problem. What they're going to say is more like this. They'll say something to help you see that there's mean value theorem involved. They'll say instantaneous rate of change, which is your f prime, is equal, or when is the instantaneous rate of change equal to the average rate of change? So they'll use these words there. They like to use that as well. So if you see instantaneous rate of change versus average rate of change, they're trying to get you to involve mean value theorem, and they're trying to get you to find the slope between the two endpoints, the derivative function, and then setting them equal to each other and finding information about that. Okay, so number one, use the function to answer the following. On the interval, what is the average rate of change? So number one, A and B, is kind of working through mean value theorem and breaking it down piece by piece here. So on the interval, what is the average rate of change? That should, I think for us, I think that would be a good thing to always do, is to do the average rate of change first before you find the derivative. Okay. I'll talk a little bit more about why that is better for us. But for now, we'll just get that algebra out of the way before we move on to the calculus. So average rate of change is simply the slope between the two endpoints. So we're going to do this. We're going to find f of 6 minus f of 2 all over 6 minus 2. Okay, you can use your calculator. But for now, if you want to just copy down the value that I find here. So f of 2, if I plug 2 into the original function, I'm going to get 12. If I plug 6 into the original function, I'll get -8. So my average rate of change, I'm going to use this abbreviation. It's just the change in y over the change in x, right? Just simply slope. -8 minus 12 over 6. Oops, sorry. Yeah, -8 minus 12 over 6 minus 2. Equals -5. So what we've done is this. Again, you don't have to sketch the graph, but I just want to show you, what we found was, between these two endpoints, the steepness between those two endpoints is -5. And because we have a smooth curve and it's connected, we know that if these 2 points is experiencing a slope of -5, this curve is going to experience that same slope somewhere along that path. So we're basically looking, asking the derivative to help us locate a point on the curve where the curve is going to experience that tangent line slope of -5 as well. Okay, so then on the interval from 2 to 6, when does the instantaneous rate of change equal the average rate of change? So we're just going to ask the derivative to tell us the location of that point. So to do that, we're going to find f prime. And that's our second task there, trying to figure out what that derivative function is. So we simply have to go through power rule there. So -2x plus 3. Now that we have our derivative function, we're going to ask the derivative to tell us the location of that point on the curve. So we now have the derivative function, and now we're going to ask the derivative, okay, derivative function, can you tell me where the graph is going to experience a slope of -5? So I'm going to put that -5 into the slope variable, and then just ask the curve, this formula to give me that location. So -5 plugs in for f prime, and then I'm just going to solve for x. So x equals 4. So this tells us that on the curve, when the curve hits that x value of 4, its steepness is going to be exactly -5, which is the x value solution that we look for. The way that they notate it is they indicate that as the C value. So C value is simply the x value location of our solution. So that's what we're going to do with all these problems here. It's multiple steps, but it is simply 2 things. Find the slope between the 2 endpoints, find the derivative, set them equal to each other, and then solve for x. So the reason why I'm going to really encourage us to find the slope is I see students have a little bit of trouble when they find the derivative first. When students find the derivative first, then you may be tempted to start to plug in the endpoints into the derivative and then using the derivative to find the slope, and then that just goes down the wrong path. So if we force ourselves to find the slope between the endpoints first, then we get that out of the way, and then when we find the derivative, that derivative doesn't end up impacting us negatively later, right? So if we get that slope out of the way, then we find the derivative, then we set 30 equal to 0. We're not using the derivative. It just gives us less chance to make mistakes with the derivative, basically. There is an important distinction between mean value theorem and intermediate value theorem. Sometimes AP exams likes to, on FRQs, they like to put these back to back within the same problem and see if students can identify, okay, wait, this one is mean value theorem and this one is intermediate value theorem. So IVT, I think, is always the easier one for us to try, because if I'm trying to guarantee on the then I simply have to identify two endpoints above and below and see if I can guarantee that y value between. But if they don't give me the function and or if they give me the function and they ask about something about the slope of that function, then we have to rely on mean value theorem. Okay, so if we're at the level that the problem is giving us, then we can use IVT. But if we're not at the level that the problem is giving us, then typically it's mean value theorem, and we have to use mean value theorem to guarantee that slope. Okay. Okay, so here are some examples that kind of highlight that distinction where you have a problem, and then one of them ends up being IVT, and the other one ends up being mean value theorem. So it says a hot air balloon is launched into the air with a human pilot. This twice differentiable function. So whenever they give that twice differentiable, that just means that you're dealing with a smooth curve. And you don't have to worry about, oh, there's a sharp turn or an asymptote or a hole. It's just going to be a nice smooth curve all the way through. We have the balloon's height in feet, and t is measured in minutes. And it says between 5 and 10, must there be a time when the balloon is 50 feet in the air? So we have information about the height of the balloon. So this one is easy to spot, right? Because, okay, my balloon starts at 0 feet, then it goes to the 40 feet, then it goes up to 70, then it goes down to 65 and goes up to 80. Can you guarantee that this balloon is going to have to reach 50 feet somewhere along that time interval? Yes, right. And this one is easy to tell because this is exactly the graph that we're looking at, and they're asking about the graph, or they're asking about the value on that graph. So this one we can just visualize, right? Between 40 and 70, it's got to hit 50 at least once. Now between 65 and 80, well, between 70 and 65, let's see, it's not going to get all the way to 50. 65 to 80 is not going to potentially not hit up to 80 as well. So we can guarantee that between 5 and 15, that we got to hit 50 at least once. Okay, it may hit 50 feet elsewhere, but we can guarantee at least once based off of our data. So we can say this. H of t is continuous. And this is IVT here. And intermediate value theorem doesn't require anything about the slope. So we don't have to make any statement about differentiability. And so we can say, okay, well, since h of 5 equals 40, and 40 is less than 50, and 50 is less than 70, which is coming from h of 15, there must be a time on this interval where h of t is equal to 50. So we're just having to go through intermediate value theorem. Don't have to worry anything about the derivative or slope because the data that we have in front of us is enough. So IVT is always going to feel easier because the data is right there in front of me. Mean value theorem is going to feel a little bit more difficult because we don't have the data in front of us and it's a little bit more abstract. So it said for number part B here, for time between 20 and 30, must there be a time when the balloon's velocity is 3.5 feet? Okay. Now, if you look, we don't have a velocity table for us to pull velocity values. But what we can do is we can create a velocity between two endpoints, right? Because we know that velocity is just the change in position over the change in time. So between 0 and 20, we can figure out what that average velocity is. And if my average velocity ends up being 3.5 feet per second, then I've got to experience a 3.5 velocity somewhere between 0 and 20. Okay.
Are you finding the velocity in between 20 and 30 or?
Oh, my bad. I said 0 and 20. Otherwise, yeah, between 20 and 30. So So we're going to be finding the average velocity between 20 and 30. And the average, if the average velocity can be 3.5, then there must be an instantaneous velocity of 3.5 as well. So we can go ahead and see if we can prove that. Let me zoom in here. So because we're dealing with something that involves the slope, we have to show that the graph is continuous and differentiable. So we have to just make a statement that we know this graph is going to be a smooth curve. So the two conditions that's needed is continuous with brackets and differentiable with parentheses. Okay, and then we just take the slope between the two endpoints, change the position over change in time. Sorry, I said 3.5 here, misread it, 1.5. The average velocity between 20 and 30 seconds ends up being 1.5 feet per minute. And so by mean value theorem, we can guarantee that somewhere on this interval, this balloon is going to reach an exact velocity of 1.5 somewhere on that time, right? I can't have an average velocity of a value and not ever reach that value on that interval. Okay, another example is, let's say you took a trip and it was 300 miles over a 5-hour period. Right? And all we know is, okay, it took 5 hours for you to complete this drive. And so your average velocity is going to be 60 miles per hour. Okay. Does it mean that you're going to be driving 60 miles per hour for the entire trip? Okay. But is it possible to have your average speed being 60 miles per hour and never hit this value at any point on the drive? Right. It's not possible, right? So that's basically mean value theorem. It says that, okay, if my average speed is 60, then I've got to have at least one point on this trip where I've got to reach that at least once, right? Maybe you only hit it once, but you got to hit it once in order for us to call that an average speed. So that's basically what mean value theorem is guaranteeing. Okay, I would just like for us to practice more with these steps for mean value theorem. So can we turn to page 12? And I just want us to practice the process, practice the steps, so that it can feel a bit more, it can make more sense. We have another theorem called Rolle's theorem, but Rolle's theorem is just a variation of mean value theorem. I think mean value theorem is more important. So if we don't get to Rolle's theorem, it's not a big deal. We can do that later. So page 12, number 39. If mean value theorem cannot be applied, explain why. So we're basically trying to see, okay, is this curve, we're going to find an average slope between the 2 points, and then we're going to guarantee that average slope, that slope is going to show up somewhere along the curve. The two conditions that we need are continuity and differentiability. This is a smooth curve, so it's a polynomial. If it's a polynomial, you don't worry about anything. It's going to pass all your conditions. So let's say our conditions here. Continuity is with brackets, differentiable is with parentheses. I'm going to write it this way so that you can always see the average velocity, average rate of change first. force you into doing that first before you find the derivative. So let's find the slope between the two endpoints. Get that out of the way before we commit to the derivative. So we'll find f of -1. We'll find f of 1. So -1 in for x, I get negative 1 minus 2, which is -3. If I plug 1 into the function here, I get 1 plus 2, which is 3. Okay, so now let's find the slope. Your average rate of change. I get 6/2, which is 3. So now that you have your average rate of change, you can now shift our attention to building the derivative. Now that we have our derivative, we're now going to ask the derivative to tell us the location where this steepness is going to occur. So make sure that whenever you find your average rate of change, that you're putting it into the f prime variable and not into the x variable, right? We're looking for the location, but we're asking for the slope. So this is going to go into your slope variable. So now we're going to just be asking the derivative to tell us, okay, between -1 and 1, can you locate a place on this curve where the steepness is going to be exactly slope of 3? So we're doing the algebra here to see if they can tell us that information. So 3 minus 2 is 1. Divide both sides by 3. I get 1/3 equals x squared. So x equals plus or minus square root of 1/3. So we have two locations where the slope is going to be exactly 3. But are both these locations valid? Yes. Okay. Both these values are between -1 and 1. And so when we get to this point of setting the derivative equal to the average rate of change, you're guaranteed at least one solution. But if you get multiple solutions, sometimes we do want to double check, right? That sometimes one solution is outside the interval, sometimes one is inside, but you're guaranteed at least one. And in this case, looks like we have two that are valid. So we call our solution C value. So we say C is equal to plus or minus square root of 1/3. You don't have to rationalize the denominator. Okay, can you try on number 40? Can you walk through the steps that we did with 39 and see if these steps make sense? So write your conditions, find your average rate of change, then find the derivative, and then set them equal to each other. Again, polynomial, so nothing to worry about with conditions. We just have to make sure we state them. So continuous with brackets, differentiable with parentheses. don't do the derivative first. If you do the derivative first, you may start using derivative in ways that's going to throw you off. So make yourself find the endpoints first. Make yourself do the algebra first. Get that slope value. In this case, the slope is 0. So now let's do our derivative process. Derivative f prime 4x cubed minus 8. Make sure that we understand what we found here is not a location. What we found here is the slope value. So make sure that you always put that 0 or that slope value in for the derivative variable and not for the x. All right, so 0 goes in for f prime. Now you're just solving for x. Cube root of 2 is just some decimal number, and that confirm that this solution is between the two endpoints. Now, if you find a solution and it ends up being outside the interval, then something went wrong. Okay, by this point, this is a guarantee. So you may have multiple solutions, and some solutions are outside the interval. That's fine, but you're guaranteed at least one of them. Okay, so if all your solutions are outside the interval, then go back to your algebra, because if we can confirm continuity and differentiability, then we should be able to have a guaranteed solution. Okay, so your homework, pages 12 through 14, all due on Monday. You know, if we didn't even know anything about Rolle's theorem, it would still be fine. We just have to go through a mean value theorem, and it's just a little bit of a shortcut for a very specific situation. But you know, Rolle's theorem, we don't need it for our homework, so we don't have to worry about Rolle's theorem for now. I'll talk about it a little bit later, but we all of our homework without knowing anything about Rolle's theorem. Okay. If you guys can get on a sheet of paper or on a separate sheet in your notebook, let me pick out some problems for us to practice with. Let me zoom in so you guys can read this better here. Okay. So just on a separate sheet of paper, this is just review for tomorrow's quiz. This is a shadow problem. Okay, you're always going to set up your shadow problems the exact same way. It's always going to be a triangle within a triangle. And your vertical components are always going to be constants. And then the base is going to be x and y. Okay, a street light is mounted on a 15-foot pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the tip of the shadow moving when he is 40 feet from the pole? Small height is to big height, and small base is to big base. Cross multiply. Find the derivative. every variable gets impacted by time. Question so far? Okay, let's gather some information here. We're looking. UIDT, we don't know. That's going to be the rate of change of the length of the shadow. And then what we're looking for is the rate of change of the tip of the shadow. So once we find UIDT, we'll just add these together, and that'll be your rate of change of the tip. Okay, so I think we have enough information to plug in and solve for UIDT, right? This triangle at that moment in time. What would be the area formula for our variables are defined a little plus y, yeah. So 1/2 x plus y, and the height is 15. So I think all we need is power rule, right? We don't need product rule to build this out because I can just distribute that through. And then find the derivative. Plug those values in. Look at your units. Area is square feet. Time is seconds. So we're using dx dt dy dt from one more here. This is a Pythagorean theorem problem. south at 60 miles per hour. What can we assign this to be? dt, positive or negative? Yes, positive. I know we associate down with negative, but in this case, this is getting larger. That vertical length of the triangle is getting larger, so we want that to be a positive. And then the other car travels west. Positive or negative? Positive. At what rate is the distance between the cars increasing 2 hours later? So 2 hours later, how far is the car going to be so that we can identify the x and the y values? What's x going to be? What's going to be this distance 2 hours later? Yeah, 50, because if he's traveling 25 miles per hour, after 2 hours, he's going to be 50 miles away from his starting point. Okay, 2 hours later, where is the second car? 120. Okay, Pythagorean theorem will get you z. And once you have z, then you have everything you need to plug in and solve for dc dt. The formulas that you need to memorize, again, those are circle, area and circumference, rectangle, triangle, square. I'll send out the reminder today. And then tomorrow morning at 7:15, I'll just create a bunch of random problems. Maybe we'll do a cone, we'll do a sphere, we'll do, be coming tomorrow morning. I'll also virtually as well. Okay. And then linear approximation, L'Hopital's rule, those are the other topics. Oh, and then particle motion, a full particle motion problem. And make sure you bring your calculator as well. Tomorrow you can use your calculator. Yes.
We do. We do. Oh, yeah, we do.
Thank you guys. Have a great day. Study for your quiz. See you tomorrow. See you, Frank.
Oh. So I will hire you. Layla, you didn't even give me your link yesterday. The people barely let me.
Bye. Have a good day. Thanks. Bye.
And you were like.
Nice. Can I see the obsession there?
Yeah, you can come in by second. Can I get a pass to it? Yeah.
Thank you.
Okay, great.
Yeah. And then screen.
All right, mark you down. Thanks, man.
With the like actual related rate problems, do we need it
Yeah, so do you have your
yeah, sorry, I was talking about like when would we have to use areas?
Oh, if it was like Thomas said, the rate of change of the area of the radius.
Wait, so like No, but like basically. Yeah. Well, maybe by Friday, 17. Okay, thank you. Same thing. Okay, thanks.
Guys, classroom copy of your package, if you don't have your own.